Good morning. My name is Nandita Singh, and I'm doing Masters in Computer Engineering in ECE department. And me and my teammate Prakhar have made the project RISC Wisk, Unleashing the Power of Software Fuzzing on Hardware for our class project. So today I will be presenting this project. Before going into the details of the project, I would like to give the overview of the presentation and the things that we will be covering in this presentation. So first, we will be discussing the importance of the hardware, how the hardware chips are made, then the importance of design verification, then we'll be addressing the bigger problem that we are trying to solve for the community. Then what is software fuzzing, the concepts like hardware fuzzing. Then we will be discussing the first phase of our research, then the second phase, and then how we have implemented the first phase and the second phase using which languages. And then finally, we'll be discussing about the third phase where we are actually evaluating our design. Then we will have our results and the comparative study. And then we will be having some discussion on the future work and the conclusion. So importance of hardware. So nowadays, every person has access to all the electronic devices. And as a user, we use the data at a very abstracted level. But what actually happens is whenever we use any application on our phones or on our laptops, it goes to an application which is actually supported by an operating system. And finally, the entire data goes to the hardware of the computer or the phone in the streams of 1 and 0. So at the end, no matter what data we are using, whether it's audio data or a video data, everything gets converted into the stream of ones and zeros and go to the hardware. And hardware is so much important in any kind of technology because till the time we don't have a compatible hardware, we cannot actually proceed in software. And the classic example for this is of an iPhone. So let's say if we have like iPhone 6 or 7, and the software keep updating on the iPhones. And as the software keeps updating, the process of the hardware becomes slower and slower because the hardware compatibility is not there to the advanced software. So that's why it is very important to keep updating the hardware. So no matter where we go in terms of technology, till the time we don't have the compatible hardware, we will not be able to take our technology forward. So basically, hardware is the backbone of any new upcoming electronic devices. And how this hardware is made. So it is made through a ASIC flow. And what happens in ASIC flow is that first a specification of a chip is given by the client. So let's say if we want to have an air taxi, then the requirements are going to come like in the air taxi, we want some features which has to be worked on a certain atmospheric pressure and so on. So these high level specifications are given to an architectural design team. The architectural design teams actually sit down and write about the entire document, what all modules have to be used, what all data processing has to be done. Later on the basis of that document, the RTL team actually codes the functionality of the modules. And then comes in the design verification team. So design verification teams makes the reference model of the actual RTL and verifies if the RTL is correct or not, whether it is actually functionally able to achieve everything that is mentioned in the document or not. After design verification, as we go ahead, we have the RTL synthesis team, where it converts all the logics into gate level. Then we have the DFT team, which will send the streams of ones and zeros to make sure that all the connections are valid. Then we have placement and routing team, which will actually place the modules or the components on a chip. Then we have static timing analysis team, which will see that the timing of the data is being matched. Then gate level simulation is the part of the cycle where we get the final necklist, but that necklist is sent back to the verification team, and the verification team actually attaches their own verification environment to the necklist and runs a test case and makes sure that whatever, like if we were able to achieve like 100% test case closure at the functional level, then even at the gate level, we are getting the same results. Once the necklist is finally signed off, then it is sent to the graphical data stream information interchange. That is where it is actually packaged and sent out to the market. So the most important thing with the hardware is that once it is fabricated, it cannot be reversed. So it becomes a very crucial part of this ASIC flow that the chip itself is not buggy. So in this entire steps, the biggest monster is design verification. And according to a report presented by Siemens Wilson Research Group in 2020, almost 40 to 50% time in a project is given to the design verification team. And in spite of giving so much of time, still there are bugs in the chip, and still there are chips out there in the market which are buggy, and that's why there are revisions every time for each and every mobile. We'll see there will be a revision, not only because there's like a new feature added, but also they used to find some bug in their previous chips. So the bigger problem that we have in our community is that even though we are spending so much of time in design verification, still it is not completely efficient. There are still some gaps, there are still some bugs that we are not able to find with the conventional techniques that are present in the industry. So to overcome that, we have to first understand some concepts such as hardware fuzzing, which has originated from the concept of software fuzzing. So first we'll just go through the concept of software fuzzing. So what happens in software fuzzing is that we have an initial test case input, which is we can create a random test case that we want to send to a software fuzzer along with the executable binary. So in the executable binary, we basically have the program that we are targeting. So for example, we want to get the password for some website, a login password. So we just give some initial combination of the password, and then we actually give the program, which is actually taking the password as the input, and we send it to a software fuzzer. Inside the software fuzzer, what happens is we run the executable binary with our initial test case. And after that, we check whether there is some coverage increase in our program or not. If there is a coverage increase, then we say that, okay, this is an interesting test case. So we store that input and we mutate that input and again send it in the cycle to run it with our executable binary. And then we keep evaluating the coverage. And then we check if whatever inputs are giving us some coverage, we just store them in one database. Whereas in case we get any crashes, then we just store those crashes in another database. So this is how a general software fuzzing happens. So software fuzzing in nutshell is about sending dynamic test cases to a program to explore the states of a program which cannot be reached by manual test cases. So by using this concept, uh, our community is evolving hardware fuzzing. So what happens in hardware fuzzing is that we take RTL design, we convert that RTL design into a software model, and then as an executable binary in a software fuzzer, we send this particular software model of a hardware. And we give the initial test case input, and entire software fuzzing keeps on happening on the executable binary of our actual hardware. So this is the concept of hardware fuzzing that we are going to implement in this project. So in this field, we already have three significant researches. So one is fuzzing hardware like software. We have RFuzz and a DFuzz. So these are the papers which are already there in the research field. Since this area is a very new area, so these are like the most significant one that we have with us for any references. So the main challenge that is faced by all of these paper is the fuzzing speed. So in software fuzzing, the fuzzing speed is very high. Whereas when we convert hardware into a software, the speed becomes very less. And the reason is, first, the RTL complexity when converted into software is very high. And second, that whatever the first initial test case that we give, the input states that we give, they are very complex and they are very large in size, which takes a lot of storage space and slows down the process of fuzzing. So from here, we will be starting the first phase of our design. And in the first phase, we will be designing our system that we would be fuzzing later. So while we are designing a system, first we have to define what do we mean by a system. So any hardware that we are trying to verify will come under the system, the designing of a system. If we are verifying interface or peripherals or a processor, so we will be creating an entire infrastructure around it, and we will be doing hardware fuzzing on it. So in our project, we will be doing fuzzing for the heart of the system, which is a processor. So broadly speaking, when we say processor fuzzing, what do we mean is, let's say we have a processor, we have a memory interface. We will be loading the memory with a set of instruction at 0 runtime. And as soon as the processor comes out of reset, it will start executing instructions from this memory. So this is like one cycle or one iteration of a fuzzing. After that, again, we'll load the memory with another set of instructions, and this thing will keep happening in a loop, and we will be keep on exploring the states of the processor. So that is like a broader insight of how the fuzzing in processor takes place. So we already have like two researches in this particular field, and we have seen that the major problem is that is the size of the memory, which basically slows down the speed of fuzzing. So as we can see in this diagram, we have a CPU which is connected to a memory, and the size of the memory is defined by the address lines. So let's say if the address line is of 32-bit, then the memory size will be 2 raised to power 32, which is 4 gigabytes of memory. So let's say we are running one test case, and one test case has somewhere around 100 instructions. Now 100 instructions will take like maximum of 400 bytes of space. But but in like conventional memory system, what happens is we are having 4 gigabytes of memory, which is used only to store one test case at a time. So basically all the other spaces is a waste space for us, but still we are having such a large memory. So the solution to this problem that we are proposing is that instead of using a conventional two-dimensional array or the conventional memory, why don't we use data structure like hash. So hash are the data structure which have like the keys and the values. So in our case, what we can do is we can use address as the keys and values as the instructions. And we can just store it in a very compact size of memory, so that if we only have to use like 100 instructions, so we just need to use a memory which is like 400 bytes instead of having like 4 gigabytes of memory. Now this will actually reduce our input state, and it will help us to fuzz in a very faster way. So our proposal is that we replace the conventional memory, which is attached to the processor, and instead of that, we replace it with a hash map or a sparse memory matrix. So this is how the integration will look like. We will have a processor, we will have a sparse memory matrix. It will be integrated in a top, and it will be connected with each other through all these buses or the memory interface. And before we go in the part where we will be fuzzing the process, we have to define like few things. and that is the parameter of a test case. So for our project, we are defining it to be of 200 clock cycles. So we are taking 200 clock cycles because by trial and error, we have seen that it is like the optimum number of clock cycles, which can explore the maximum states even in like five pipeline stage processes. So if we have like 200 clock cycles, then at least two clock cycles are used to get the processor out of the reset. So that means we are left with 198 clock cycles. And each instruction takes almost two clock cycle to execute. So the number of instructions that we will be giving in one test case will be around 99. So this is the baseline that we are setting up for each iteration, and we will be moving forward keeping these two things in mind. Okay, so now the two fundamental concepts that we are trying to incorporate are, number one, that the memory has to be a compact memory. So instead of using like 4 gigabytes of memory, we will be using just 400 bytes. So that will reduce the storage space significantly and improve the fuzzing speed. And the second concept that we are trying to incorporate is to have the valid instruction for all the clock cycles. So we want to explore the maximum functional state of the processor. So we have to make sure that if we are fuzzing, if one test case is like for 200 clock cycle, and if we are fuzzing for 200 clock cycles, we are giving, let's say, 100 test cases. So each test case is exploring the functional state of the processor. So which means that we will be giving it only and only valid scenarios, and we will make sure we will constrain our instructions in a way that every time it is landing up to a instruction memory where it is getting a valid instruction and not some random value, so that it do not go into an exception state. Because if the processor is hit with some random value which is not like a valid instruction, it just indicates interrupt and it goes into a trap state. So we don't want our processors to go in that state, and that's why we will always be giving it valid instruction. So these are the two fundamental concepts that we will be holding. And while implementing our design, so how we will, I will be explaining my design is we will be building our design from the scratch and all the challenges we will be facing and the solution to it, and we'll keep on building. And finally, we will get to the entire design of our first phase. So the first challenge that we faced was storing a value at random address. So let's say we have a processor, we have a memory interface, and we have loaded our memory with like 100 instructions. So the at 00 we have, let's say, arithmetic operation. At 04, what we are doing is we are storing the value of register x3 into a memory location 0xc. Then we are having another logical operation. Then when we come to 0c, we are saying that the value which was there in x3 is getting updated at 0c. Now this is a random value. This is not a valid instruction. So initially the valid instruction that we have loaded in the memory is updated with some random value. And we won't want this, because after this point, what will happen is the processor will go into a state from where we cannot retrieve it unless and until we go and reset it. So since we don't want this, because this is not giving us any of the functional state of the processor, so we have to prevent these type of scenarios. So to provide a solution to this problem is that our processor will be connected to the sparse memory matrix in the memory model. So in the memory model, we will be integrating an intelligence, which will be segregating the instruction memory and the data memory. So we will be dividing the memory completely into half, and any address which will be lying between 0 till FFC will be considered as the instruction memory, whereas any address which will be above them would be data memory. So now we will be constraining our instructions that if it has to jump, it will jump only and only in the instruction memory. So in the previous example, as we have seen, if we are storing a content of this particular register into some address, this address has to be a data address. It cannot be an instruction address, because we do not know the content of this particular internal register. So this was the first challenge that we faced. The second challenge was, what if the program counter reaches a non-existence memory location? So let's say the processor starts booting up from address 0, then it goes to address 4, goes to address 8. And at address 8, we have an instruction which branches to a memory location which is at 180. We have filled up our memory with like 100 instructions, and we go to address 180, 184, 188. Right after 188, even though we have only gone far for like 14 clock cycles, but after 188, it will try to access an address which do not exist, and that would lead to a crash. So then we will convert our entire hardware into software, and in software, whenever we are trying to access any memory location which do not exist, it gives us segment fault. So this type of problem will always land up giving us the segment fault. So to prevent these type of problem, what we are going to do is, whenever there is like a read or we are actually approaching a address location, then based on the address, we will be checking that whether it is an instruction memory address or a data memory address. Depending upon the address, either we will be creating a new entry and writing a constraint instruction into that new entry, or if it is like a data memory, then we will be writing a random data into this particular memory. So generally, we are constraining our fuzzing only in the instruction memory. So there would be very few scenarios where we will be actually jumping to the data memory, and that would be when there is a load instruction. So what a load instruction do is it captures the value from the memory and stores it into the internal register. So when it captures the value from a memory, um, and there is no memory available. So what we do is we create a new entry, we fill it up with random data, and then we just retrieve that data as a load instruction. So this is the algorithm that we use to prevent any kind of segment fault. And before going, and as we have mentioned that we have to have like constrained instructions. So this is like a RV32I instruction formats that are used to build any kind of micro ISA micro architecture. So as we can see there, we have opcode, we have functions, we have immediate address, and the internal registers. So many of the processors define in those, the internal registers are generally like 32 from X0 to X31, whereas we have like some opcodes. So opcodes is like a bigger umbrella which defines whether an instruction is arithmetic or a logical type, or it's a branch instruction, store instruction, or a load instruction. And then these functions basically pinpoint that which exact operation is happening. So this is the example of a basic load and store instruction. Now in load and store instruction, the type of uh, addressing that we use is register indirect addressing. Now this type of addressing will be giving us some challenges. For example, what happens is in the internal register, we save the base address. That base address is added to the offset, and then we create a relative address to where we jump and um, get our value from, or we store our value from. So we always have to make sure that the relative address is either word aligned or byte aligned or half word aligned, depending upon the instruction it is being used. So in order to solve these two problems, let's first solve the simpler one, which is the offset. So first, in those terms, first we will be defining what is word alignment, byte alignment, and half word address. So let's say if our memory is word aligned, and if we are having like a load as word aligned, so that means we are going to retrieve a word from a memory. That means a word is equivalent to 32 bits. That means 4 bytes of data. So anytime we have to give an address for a word retrieval, we have to make sure that it is divisible by 4. The address is divisible by 4. So it's going to be 0, 4, 8, 12, then 10, 14, 18, 13, and so on. Because we are retrieving 32 bits. Whereas if we have to just retrieve a single byte, then the address can be 0, 1, 2, 3, 4, 5, anything. And if we are trying to retrieve a half word means 16 bits. 16 bits means 2 bytes. That means our address has to be 0, 2, 4, 6, and so on. So in this, we can say that whenever any offset or any instruction have to be word aligned, then the last two bits are always 0. Whereas if we are actually focusing on half word address, then the last bit is always 0. Whereas in byte address, I think we can just have any address and it would work. So in order to make sure of this thing, what we do, we write a constraint block and an instruction generator. So the constraint block is a block which is written to basically constrain our instruction. So first we generate all these constraints, and then we send those constraints into a constraint generator to actually form our instruction in a particular format. So when we are giving any constraint, so we will make sure that the offset, depending upon what instruction we are using, is either word aligned or half word aligned or byte aligned. So for byte, we do not have to put any constraint, but for word, we have to make the last two bits equal to 0. So we can randomly create an offset and then just simply AND it with value, which is like FFFFF, and the last two bits are 0, 0. Whereas for a half word alignment, we can just have to make the last bit equals to 0 by ANDing it to 0. So this is the constraint that we are going to put in our offset. But this is not just the only thing which is going to solve a problem, because since it's an indirect addressing, so we have to add the offset to the register value. Now the register value could have got updated. So since we will be giving some random instructions to the CPU, so there is high possibility that that a register which is holding the base address would have got updated by some add instruction or any arithmetical or logical instruction or a store or load instruction. So what happens when indirect addressing comes into play? So as soon as we come to know, so once the constraints are generated, we know that which particular instruction we are going to make. So in this memory, we put an intelligence which tells us that, okay, if it is an indirect addressing mode, then we are going to save that instruction on the next address, not the current address that we are going to retrieve, but on the next address. Whereas on the current address, we are going to update the register, which will be holding the base address. So in order to do that, what we do is we use a instruction called ADDI. So ADDI is going to add the immediate data to X0. Now X0 is hard-coded in all the cores to 0. So 0 adding to any random value is basically going to update the value in RD. Now RD is going to be the register which is going to have the base address. So in order to make sure that it is word bound and half word aligned, what we are going to do is this random immediate data that we are going to generate, we are going to make sure that it is word aligned or half word aligned or byte aligned. And then we can send the data to RD by using this ADDI instruction. And in the next instruction, we can have like an indirect addressing mode. So by doing these solutions or using these algorithms and putting this intelligence in this memory model and constraint blocks, we will be able to get an indirect addressing mode. Now, the next challenge that we face will be with the relative addressing mode. So what happens in the relative addressing mode is that PC adding the offset value is going to give us the relative address, where either we are going to have some jump or branch and so on. So the basic example that we have here is that at 0, 0, we have some arithmetic operation. Then in the next address, we are jumping to some value, which is inside instruction memory. So we are going to instruction memory, and then we have some address, and in the next address, we are getting a relative address mode instruction. Now this relative address mode instruction is going to get offset, which is going to get added to the PC value. So right now the PC value is going to be E014, and let's say the offset that is generated is 2BAC. Now, while adding these two, the relative address that we will be getting will be 10BC0. Now, this is going to land us up in a data memory, and we don't want to go there, because if we go there, then even before our 200 clock cycles are over, we are landing into the data memory zone, and where we'll just be getting some random data. And that is something we don't want, because we want to explore the functional states. So what we do is we constrain our offset. So the algorithm that we use is the PC value minus the end of IMEM. Sorry, the end of IMEM is going to minus the PC value, will give us the range. So we can have any value selected between 0 and that range. And then we are just going to make it word aligned. And that particular offset is the offset that would be added to PC, and it will make sure that it never goes in the data memory. So there will be one problem that would occur is, what if we are landing up too near to the end of instruction memory? So that particular problem we will be solving in challenge number 6. So the another challenge that comes up to us is about writing into a memory violating our fundamental concept. So first we'll talk about the read, so that we are clear what is happening in the read, and then we can discuss how the write is preventing us to maintain our fundamental concepts of fuzzing. So we have a processor, we start booting from the 0 address, and we keeps on loading the instructions. And whenever there is like a load instruction, then either we load instruction from the instruction memory, or if the address given in the instruction is of a data memory, then we'll go to data memory. If there's no already existing value, then we will just create a random data, a new value there, and we are going to load that random value in the internal registers. And that's how the read operation will always happen. Now, in case of a write, so let's take this example. At 0 address, we are adding the value of x0 and x3 and putting it into x1. Now, in the next address, we are storing the value of x1 into a memory address 0xc. So right after 2 more cycles, we will be storing a random value in our instruction memory. And doing that is basically violating our first fundamental concept, where we want to explore as many functional state as possible of the processor. So doing this will create a problem for us. So we cannot write a random value in the instruction memory. So to prevent this, what we can do is we can put a constraint that, okay, let's just go to the data memory, and just write any value in the data memory, and then we are good to go. But if we do that, there's another problem that comes into picture, and that is, now the write is only confined to the last 16 bits of address. So we have divided the memory into 2 parts. Now, if we are constraining, then the write will only and only happen in the data memory. We will never be able to toggle or to have the coverage for writing in the upper half of the address. Whereas with the read, that was never the case. We were having the load instruction, which was able to load either from the data memory or from the instruction memory. But with write, we are constraining it. So in order to avoid this constraint, what we do is we create a secondary memory. So in our memory model, we will be having 2 memories, and we will check if it is a read operation, then we will be key fuzzing from our primary memory. But if at all it is a write operation, we will be writing it into a secondary memory. So in that way, we do not have to constrain the write to a particular section of the memory. We can save the states of the internal register, and we just have to use another secondary memory to just keep the states getting updated, and it can all work out for us. We have the full range of write as well as storing all the internal states of the register. And then comes the challenge 6, which is the memory bound with respect to the clock cycles. So in this case, let's take the worst case scenario. We are at 0, 0 address, and at the first address itself, we have a branch instruction, which is asking us to jump to FFF0. After going to FFF0, we are having some instructions executed. And right after like 4 addresses, we are going into the data memory. Now, if we go to data memory, again, we won't be able to fuzz for the entire duration of the clock cycle or the test case. So how do we solve this problem? To solve this problem, we shrink the end address of the instruction memory for the sake of calculation of the offsets. So what do we do is, first we see, like, out of these 200 clock cycles, how many clock cycles we can reduce. So we know that 2 clock cycles will be required to take the processor out of the reset, and 1 instruction will be the bare minimum instruction used for any kind of jump. That is the worst case scenario. So now we have 196 clock cycles. That means the total number of instructions which require the location space is 98. So what do we do is we are just going to shrink back the end address of the instruction memory. And this concept is going to be used for all the offsets which are basically giving us any kind of branch or jump instructions. So now the range will always be from 0 to end of the new memory. And in case if it's like a relative address, then minus PC is going to give us the range, and then that particular value can be word aligned. And we can just move ahead with these algorithms. So this is the end of our first phase. And this is the overall system that we have built. We have our processor. We have our reset generator. In the top, we have a memory model integrated. We have our sparse memory matrix, instruction memory, data memory. We have a DPI interface from where we are connected to a constraint block and instruction block. And this entire thing is going to be in a C test case from where we will be generating the clock and giving it to the processor. And then this entire test case is sent to a tool called Veriliter, which basically converts the entire hardware into an executable binary. So this is the end of our first phase, and we are finally getting an executable binary that we can send to a software fuzzer for further fuzzing. So in the second phase, we will be doing software fuzzing of the hardware. So to do so, we need to have the three basic elements. One is the executable binary, second is the input initial test case, and then a mutator. So what is the executable binary? So the executable binary is basically the converted hardware, and we know that we want to load our memory with the initial test case at 0 runtime. So this executable binary will always ask for like a test case to be loaded in the memory. And this will be our test case, a combination of address and instructions. Then comes our initial test case. So what we are doing is we are trying to make sure that our initial test case have the instructions from all the umbrellas. So when we are writing our first test case, we are making sure that if we have a pool of 10 opcodes, then instruction uh, from each opcode is there. Like at least there has to be like one instruction which is from a particular opcode. So if we have 10 opcodes, so we at least have 10 instructions of each opcode. And then we have a mutator. So in software fuzzing, what happens is we have a mutator which changes the input little bit. And how it changes is either it will trim the input or it will perform some logical or arithmetic operation on the input, and then it will keep on sending those input to the program and it will keep on checking the coverage. But in our case, we have a processor. Now, processor cannot have like any invalid values, otherwise it will go into a trap state, and we don't want that. We want to explore its functional state. So in order to only explore its functional state, we have to write a custom mutator. So now the custom mutator is basically a feature which is given to us by AFL++, which is a software fuzzer, which allows us to write our own custom mutator. And by writing our own custom mutator, we are trying to make sure that the integrity of the instruction is made. And we have to also set the percentage of mutation that we will be requiring to do for each test case. And this number we have taken out from the studies that if we have like a smaller number of mutation, then we tend to get a larger coverage. So how our custom mutator works is, so let's say for the simplicity of the calculation, we have 100 entries, or we can say 100 address and instruction values. Now, first we calculate the number of instructions that should be mutated based on the mutation percentage. So let's say our mutation percentage is 3%. Then 3% of the 100 instruction will give us 3 instructions. So now we know that out of these 100 instructions, we have to mutate 3 instructions. Now, which 3 instructions we are going to mutate? So randomly, we are going to just generate any 3 random values between 1 to 100. Whatever value we get, the instruction located at that particular indexes or values will be the one which will be getting mutated. Then once we have selected those particular locations, we are going to segregate the address and the instruction. Then we are going to disintegrate the instruction. Okay, so I have taken one example over here. So let's say I have like got a I-type instruction. So I know that in my I-type instruction, on the basis of the opcode, we can actually identify which type of instruction it is. And once I know that it is an I-type instruction, I'm going to disintegrate it and going to retrieve the fields of the instruction. And after that, let's say I'm going to decide like which particular field I need to mutate. So now I'm going to randomly select a parameter which I need to mutate. So let's say in my random generator, I get RS1. So if I have to change RS1, and the value of the RS1 is X5, which is written in the instruction. Now I'm going to take any other internal register other than the X5, and I'm going to put it in the instruction, reel it back, reconstruct the instruction, and put it in the mutated file. So this entire cycle will happen 3 times since we are doing 3% of mutation. And then finally, we will be returning a mutated file. And then that mutated file will be again run with the executable binary. So as we can see here, we will be having executable binary, initial test case. We will be sending it to a AFL++ engine. It will run these 2 things together. It will check for the coverage. If it has input which is giving us interesting test case, that means some increase in the coverage, we are going to store that test case. If there is no increase in coverage, we are just going to discard that particular test case. And if we have an interesting test case, we are going to give it back to the mutator, where it will change it a little bit, and again it is going to give it to the AFL++ engine to run it with the executable binary. In case of any software crashes, then we are just going to report it in a crash bin. So now if we talk about the implementation, so we have implemented these two phases on 5 RISC cores, PicoRV, Sudar 135, and MOR 1KX. And for all of them, we have created a memory model, we have created a constraint block, an instruction generator, and a custom mutator. Now let's talk about the secret sauce, the memory, the hash that we have actually implemented. So the biggest challenge that we faced was to integrate a hash map with Verilog, because conventional memory works on the sensitivity of a clock and a reset with the memory interface. Now, integrating a hash which follows all these uh, signals was a challenge. So what we did was we implemented our memory model in System Verilog. Excuse me. So System Verilog is a language which is made on top of Verilog. It has the hardware descriptive language capabilities as well as the software data structures and OOPS concepts. So this is kind of like a superset of software as well as Verilog, and this particular language is mostly used for design verification. So what we have done is that we have done a memory modeling using this particular language, and as we can see in this example, we have taken a module, and in this particular program is written in System Verilog, and we have taken a associative array, which is like a hash equivalent in the System Verilog. And as we can see in the memory, we are putting some values like 0, 1, 10, 9, 8, 7, 0, 0. We are loading it with some value, and then finally we are printing the content and the size of it. And we see that even though the values are away from each other, still the size of the memory has only went up to 4. So if we use this particular memory with our processor, we will be able to make a really compact memory. So these are the types of interface that we have for the respective cores. So we had a general memory interface for PicoRV and Sudar cores, whereas for MOR 1KX, we had a wishbone interface. And we also have like a common bus or a separate bus. So common bus means that we only have like one bus and one memory is integrated to the core, and we have to write all the constraints to segregate the instruction and data memory. Whereas where we have like a separate bus, so in that case, we will be having like two memory bus, which will be getting connected separately to the instruction memory and to the data memory. Okay, now talking about the constraint block and the instruction generator block. So these two blocks we have written in a C language, and which is connected to the SV model using a DPI direct programming interface. So we could just exchange information between these two blocks, and we can create the instructions that we want to. So the reason we need to have this interface is because when we are creating a constraint, we need to get some information such as the program counter value. So in case of creating the offset for a relative address mode instruction, we need to know what is the PC value. So in those cases, we're saying like the PC value as the input to the constraint block. The constraint block creates all the parameters, it is sent back to the SV. Then SV calls the instruction generator function, and it just asks it to create particular instruction in a particular format. And then we can just create a new entry in the associative array, and then the processor can just read from that memory location. So the final feature, the final thing that we implemented was a custom mutator. So we have written the code in Python, and it was easier to write, and we also had like a inbuilt APIs in the AFL++, which helped us to write this particular custom mutator. So our custom mutator is built on Python language. And now we are entering the third phase of our project, and that is the evaluation. So at the end of the day, all we care about is the Verilog code of the processor that has been covered. So what we do is we have the database of all the interesting test cases, which has provided us with the coverage increase. So we take those test cases, we run it with the executable binary, which has the coverage enabled. So we write a Python script, which will pick up each test case on the basis of the incremental time, run it with the binary, and stores the coverage report. Then we write a bash script, and incrementally we will be merging the coverage reports. So at the end of it, we will get an annotated RTL, which will basically be telling us all the lines that have been covered and which are not covered. And we will be getting the incremental coverage report. After that, we can just write a simple Python script to plot the coverage over time graph. So this is one example of the coverage over time graph that we have. So this I have taken off Sudar 5. So as we can see here, on the x-axis, we have time in the log scale, whereas on the y-axis, we have coverage in the percentage. So we see like after a certain amount of time, we get a test case which gives us a little more of coverage, and we see like a change from like 42% to 45%, and then we go above and above. And as we can see, the time increases, the coverage also keep on increases. But after a certain time, we see that the coverage do not increase anymore. It becomes like a constant line. So the reason for that is that in our Verilog code, we take the default settings, and there are some type ifs which if not defined, will not be covering a certain line of code. So either we can just go extensively through all the code of the course and then we can just disable the coverage there, but it would be a very taxing job. Or the other way to get like a higher coverage is to create a netlist of the processor and then just add it to the memory interface and then do fuzzing on top of that. In that case, we will get the coverage which is like even higher. So, but these are the reports which we have got like just to get the line coverage when we have not disabled the lines which no matter how much fuzzing we do will never get covered because they are disabled by the type divs. And these are the plots from Sudar 1 and Pico RV32. This is for Sudar 3 and more 1KX. And now we will be talking about the comparative study. So we do have a paper in which we are fuzzing hardware like software, which is having a very good mechanism of fuzzing all of these peripherals. Whereas we have two papers, RFuzz and DFuzz, which is there to fuzz the processor. And according to their paper, the DFuzz has proven to be 40 times faster than RFuzz. And DFuzz on evaluating more 1KX had the fuzzing speed of 0.41, whereas our system had the fuzzing speed of 449.7 for more 1KX. The other processors were not fuzzed by DFuzz, but alone with like more 1KX, it's not like 1000, but like 609 times better fuzzing speed compared to the state of the art tools that we have. And as far as the extendability of a tool is concerned, so any processor, irrespective of their microarchitecture, if it is built on top of RB32I and RISC 1000 architecture, if it understands those instructions, we can just directly integrate in our top file and call it in a C-test, and we can convert it into a software model, and we can use our custom mutators to mutate them. As far as future work is concerned, so how we can extend this work is by writing fuzzer custom mutators for 64 bits of processor. And as we can see, we already have like a state of art for all the peripherals, and we have got like a really good performance at the processor level. So what if we integrate all of them together in a system on chip and then we try to fuzz it? So I think that would be a very interesting future work in this area. And finally, I want to summarize by saying that we have built a 32-bit CPU hardware fuzzer that is 609 times faster than the state of art hardware fuzzer. Thank you.